After watching these videos lectures, students will be able to identify the basic types of quantum numbers and how they identify specific information about electrons within an atom. So when we're dealing with many electron atoms, we're dealing with the need, or we have the need to identify specifically where those electrons are primarily residing. And we've talked about Schrodinger's equation. We've talked about the solutions giving us items or structures known as orbitals. And we know that each solution to Schrodinger's equation give us what's known as a set of quantum numbers. And this describes the solution to the equation, or the orbital, in specific ways. Something that we need to understand about each electron is that the quantum numbers associated with Schrodinger's equation have to be unique for each individual electron. So that brings us to the Pauli exclusion principle, which basically says that no two electrons can have the same set of 4 quantum numbers. And we're going to talk about these quantum numbers. Quantum numbers are basically, can be compared to a, kind of like a ticket to a theater or to a concert. They tell you the location in the building that you'll be sitting. They tell you the row. They tell you the seat number. In that same way, the quantum numbers tell us the seat number, the row, and the location in the atom for a specific electron. So the first quantum number that we're going to look at is the principal quantum number. It is represented by n. The principal quantum number indicates the energy level of your electron, so where it is with respect to the nucleus. It's going to exist as a whole number, so 1, 2, 3, 4, etc. The principal quantum number also dictates the size of the orbital. The larger your orbital, or the larger your principal quantum number, the larger your orbital is going to be. And we see this trend here. You know, the 1s orbital, it's closer to the nucleus. There's less things in between it and the nucleus, so it's going to be smaller than the 2s, which is going to be smaller than the 3s, etc. So basically, this is your quantum number. This number also corresponds to the period numbers that are associated with each row on the periodic table. So, you know, your n equals 1, that's your first row, n equals 2, second row, 3, third row, etc. So the angular momentum quantum number, or your L quantum number, indicates the energy sublevel. So basically, it's a more specific determination of the orbital type that you are discussing. So the principal quantum number indicates the energy level and whatever is correspondingly possible within that energy level. However, the angular momentum quantum number tells you the shape of the orbital. And of course, the number of shapes possible for each energy level is actually dictated by n. So the higher in energy you go, the more possibilities you have in terms of orbital shape. So the way we figure out our angular momentum quantum number, our shape, is we first look to n. So we're going to have a shape that corresponds from a L equals 0 value all the way up to n equals 1. So let's say that our principal quantum number, n, is going to equal 3. So our possible L values associated with n equals 3 is going to be 0, 1, and 2, because 3 minus 1 is going to give us 2. So the shapes that correspond to these angular momentum values is going to be your S, P, and D. So when I get to the n equals 3 quantum number, principal quantum number, these are the possible shapes, the S, P, and D, for that specific quantum number set. In contrast, if we look at n equals 1, okay, the angular momentum quantum number possible is only going to be 0, because 1 minus 1 is 0. So in this case, the only shape possible is an S orbital, which relates directly to our orbital filling and things of that sort when we use the periodic table. So the third quantum number that we need to consider is the magnetic quantum number, so M sub L. Okay, and we see that here, m sub L. Basically, your magnetic quantum number indicates the orientation of the orbital that you're looking at. Remember, we talked about p orbitals and d and f orbitals all having specific orientations around the x, y, and z axes. And so what this tells us is the specific orbital in each sublevel that we're looking at. So we can decide, are we looking at an electron that's in the px, py, or pz orbital? And basically, in order to get our values, we actually need to utilize our L values that we just discussed on our last slide. So actually, this should be negative L to positive L. Okay, right? So if let's say I have I said n equals 3 on our last slide, and that gave us L possibilities, so it tells us orbital possibilities of S's, P's, and D's. And let's say I only wanted to look at the L possibility. Okay, so we know that L is equal to 1. So in this case, my m sub L values are going to be -1, 0, and +1. So, we might assign our -1 orientation to our px, our 0 to our py, and our +1 to our pz. So the orbitals are going to be assigned a specific m sub L value that associates with the directionality of each. So that'll allow us to say, hey, the electron is in the px orbital, or the py, or the pz orbital. Our last quantum number that we're going to look at is our m sub s. Okay, and basically it indicates the spin of the electron. So we look at an electron spin as being either +1/2 or -1/2. So is it rotating clockwise, or is the electron rotating counterclockwise? So orbitals hold electrons and they spin in opposite directions. So if we look at, I don't know, let's say we have a 1s orbital. Okay, we know a 1s orbital will fit 2 electrons. So one electron is going to go as a +1/2 spin. If I put a second one in there, it's going to be as a -1/2. So +1/2 is represented by this little up half arrow. -1/2 is represented by this downward facing half arrow. So basically, the electrons want to minimize their repulsion. So when you put 2 electrons that have opposite spins, it makes it where the repulsions are less than if I were to put something like 2 spin-up electrons. So basically, what you end up with here is a way to differentiate electrons that are in a specifically identified orbital. In this case, we've already identified the principal quantum number. We've indicated that it's a 1s orbital, so n equals 1. We've indicated our L value in this case because L equals 0 here. Subsequently, our m sub L value is also 0 because remember our m sub L value is dictated by our L value. So s orbitals are spherical, so there's only one option. And then we have indicated the difference between these 2 electrons because one is spin up and the other is spin down. So these 2 electrons have 3 of the 4 quantum numbers. They share them, they're exactly the same, but it's this 4th one that differentiates the 2. So what we have here is just a diagram that kind of allows us to visualize what becomes available as we increase our quantum numbers. So n equals 1, notice the s is the only orbital that's available to us. If we look at n equals 2, that starts to expand the number of orbitals that are available. N equals 3, we have more, n equals 4, etc. Okay, so obviously the larger our principal quantum number, the more orbitals that are available for usage for electrons to reside in. So let's look at a little bit of practice. So for an n equals 5, remember n is your principal quantum number, determine the number of allowed sublevels, okay, so the different values of L, okay, so or the types of orbitals, and give the designation for each. Okay, so if I'm going to look at this, so my n, n equals 5. This is my principal quantum number. And they want me to tell them what kind of orbitals, so s, p, d, f, etc., are allowed in this type of principal quantum number subset. Okay, so if I want to determine that number of subshells, I need to look at the my L value. I need to figure out what my shapes are going to be. So remember that your L values go from 0 all the way up to n minus 1. So in this case, your L value is going to be 0, 1, 2, 3, and 4. Okay, so what do we have here? Okay, well, we know our L equals 0 corresponds to S's. Our L equals 1 corresponds to P's. Our L equals 2 is D's. Our L equals 3, F. Okay, and 4 is G. We haven't talked about G orbitals. You don't need to worry about them, but that's what's available for you for this type of problem. So we have a set of subshells. We can identify the type of orbitals that could potentially be used to hold electrons in this specific example. So now this brings us to identifying incorrect orbital designations. And we need to think about what the orbital designations mean in order to figure out if they're incorrect or not. Okay, so let's go ahead and let's look at our first example, the 1s. Okay, in this case, n equals 1 because they told us. Now, an s orbital, right, is going to correspond to an L equals 0 value, right? We've discussed this in the previous slides. Now, is this L equals 0 a possibility given our principal quantum number? And if we look at this, okay, L is dictated by 0 all the way up to n minus 1. You guys remember this by now, I'm sure. Okay, so n minus 1 in this case is going to be 0. So L equaling 0 is completely acceptable with respect to this. So this is a correct designation. So let's go ahead and let's look at 1p. Is this a possibility? Okay, so 1p, our principal quantum number in this case is 1. L in this case also equals 1. Is this 1 a possibility for the L equals 1? If we look at that, remember, L is equal to 0 all the way up to n minus 1. 1 minus 1 is 0. So is L equals 1 a possibility? No, because the only possibility for the principal quantum number of 1 is L equaling 0. So s orbitals are the only thing available. So this is an incorrect designation. Okay, let's go ahead and let's look at 7d. Okay, 7d. So that's the orbital that's being designated. Is this a possibility? Okay, n equals 7. L equals, we have s's are equal to 0, p's are equal to 1. So d's must be equal to 2. So in this case, L equals 2. Now, is 2 a possibility? Well, remember, our L values are equal to 0 all the way up to n minus 1. And in this case, n minus 1 would be 6. So all the 0, 1, 2, 3, all the way up to 6. Okay, so this is a possibility. So this is okay. The 7D is an acceptable designation. Okay, 9S. Okay, is that a possibility? Same approach, right? So 9S, n equals 9. L equals 0 in this case, and we do know that L is going to be from 0 all the way up to 8. So completely acceptable. 0 is a possibility. Okay, so this is acceptable. 3F, let's look at this. N equals 3. F equals 3. Okay, so L equals 0 all the way up to n minus 1. In this case is 2, right? So the F is not an accessible orbital type for this specific example. Let's see, 4F, let's look at this. N equals 4, L equals 3, Okay, so L is equal to 0 and everything between up to 3. So 4F is acceptable. Okay, and last but not least, let's do this 2D example. 2D, N equals 2, L equals 3. Okay, L is equal to 0 all the way up to N minus 1. In this case, that would only be up to the p orbital, up to 1. Okay, so 2D is not an option. Okay, so remember that your principal quantum number dictates your shape and orbital type that is possibly accessible. So you want to make sure that you're paying attention to this rule set, and that'll allow you to identify if the orbital designation that you've been given is acceptable. You take the same kind of approach to the question down here. However, in this case, we've been given an additional orbital definer that is going to force us to pay more attention to the set of quantum numbers. Okay, so in this case, basically, once again, we're trying to figure out if we have a set of quantum numbers that are acceptable, and if we do, is what's wrong with, if we do not have an acceptable set, what's wrong with the set, basically. Okay, so remember, everything else is dictated initially by your n value. So n equals 2, we know that for n equals 2, that's going to dictate our L values. So for n equals 2, we know that the L values that are possible are everything from 0 up to n minus 1. So in this case, we have 0 and 1 as possibilities. Okay, so n equals 2, L equals 1, so far that's acceptable. Now, can we have m sub L values? So remember, our m sub L values go from negative L all the way up to 0 up to positive L. So in this case, negative 1, 0, positive 1. Is that a possibility? Yes, that's what we have here. So this set is completely acceptable. Okay, so set A is fine. Let's go ahead and look at question number 2, or B, excuse me. So n equals 1 in this case. So L in this case can be from 0 to n minus 1. N minus 1 in this case is going to be 0. So we immediately have a problem with our L value, right? The only possibility that we have for the n equals 1 principal quantum number are s orbitals. However, this quantum set that we've indicated here involves a p orbital. So that's our initial problem. We could look at the m sub L value, but it's not necessary because the L value is already what has caused the problem. So this set here is incorrect. Okay, if we look at our next example, n equals 8. So remember, our L values can be anything up from 0 up to n minus 1, which will be 7. Okay, so the L value here is acceptable. Now our m sub L values are dictated by our L values, so we have everything from negative 6, negative 5, negative 4, negative 3, negative 2, negative 1, 0, all the way up to positive 6. So this set of quantum numbers is acceptable. And then D, if we look at D, n equals 1. Okay, L in this case equals everything from 0 to n minus 1, which would be 0. So our L value that we have so far is acceptable. Now our m sub L value, remember, is negative L to 0 to positive L. In this case, though, we only have 0 because that's the only L value that we have. So this set right here is incorrect because the m sub L value is not acceptable. So basically, they're all interrelated. They're dictated. Each one is dictated by the other. So I want you guys to make sure that you're paying attention to how they basically build upon each other. The n value dictates the L value. The L value dictates the m sub L value. And then you only have 2 options for your m sub S value. So one additional thing that I want to point out here is that when we're looking at say an n equals 2 quantum number, and we're looking at the L values that correspond to that. So remember, L is equal to in this case 0 and 1, so that's an s and p orbital. What that is saying is that when I'm looking at an n equals 2 level, the two possible orbital types are s's and p's. I can have a 2s and a 2p orbital there. When I go and I'm calculating my m sub l values, okay, my m sub l values are actually going to be separated for both the s and the p orbital that we are looking at that correspond to the n value for that orbital set. So what do I mean by that? I mean that the L values that you have here, those are representing obviously that you have s and p orbitals. We use the values here to represent my m sub l. So my m sub l for the s orbitals obviously is going to be 0. My m sub l for my p orbitals are going to be -1, 0, +1. Because remember, your m sub l value dictates your directionality. S orbitals are spherical, so they don't have directionality, so m sub l equals 0 is what you expect. The p orbitals, on the other hand, have a directionality that goes around the x, y, and z axis. So we would expect the 3 different orientations that correspond with each of these. So I just want to make sure that we're looking at our L values correctly. Now, this is also in contrast to when I'm given a specific set. So if I give you, let's say I say, give me the quantum numbers for this 2p orbital, okay? Well, first of all, you do know that the n value is equal to 2 because you've been given the energy level. Now, the L value, you're not going to use the approach of writing down everything from 0 to n minus 1. The reason why you're not going to do all of that is because the type of orbital has already been designated. They've told you have a 2p orbital. Okay, so p orbitals correspond to an L value equal to 1. Okay, so because they've already specified which orbital they're discussing, you don't take the approach that you did up here. So you don't do the 0 all the way up to n minus 1. Okay, now with respect to your m sub l value, okay, I haven't specified as if this is a pz, px, or py orbital. So any of the options, the -1, the 0, or the +1, those are all possibilities. So any designation could be considered acceptable. So just make sure that you're differentiating between these two approaches. This is a more general, like, hey, what are all the possible orbitals available to me? When you're given a question where you're told the orbital type, you have been given a little less leeway when it comes to the identifying quantum numbers.